Welcome back to the Deep Dive. Whenever we talk about shifting to renewable power, there's always this fundamental question lurking underneath. Is the system actually sustainable from an energy perspective?
Right. Does it produce like substantially more energy over its whole life than it costs, energetically speaking, to build it, ship it, install it?
Exactly. We're not just talking dollars and cents here,
No, this is about the actual energy balance. And we usually use two key metrics for this. First, there's the energy payback time, or EPBT.
which is how long it takes for, say, a solar panel to generate back the energy used to make it in the first place.
Precisely. And second, maybe even more importantly, is the energy return on energy investment, ERI.
And today we're diving deep into a really significant paper, though it's a bit older now, from 2016. It's called Energy Learning Curves of PV Systems. And it tackled exactly how fast solar was improving on those two fronts, EPBT and ERI.
Yeah, that study was quite groundbreaking at the time because it drew this, well, unexpected connection. Our mission today is basically to unpack its core finding,
Which was,
that the huge amount of energy needed to manufacture photovoltaic PV systems, it doesn't just decrease randomly over time.
okay.
It actually follows the same kind of predictable pattern, a learning curve law, that economists usually use to track how financial costs drop as production scales up.
Huh. So applying economic rules to energy physics?
Yeah.
That's neat. A shortcut to understanding solar's energy future, essentially.
That's the idea. But maybe let's just quickly define energetic sustainability again. So EROI, it's the ratio, right? Energy you get out versus the energy you had to put in.
And why is that ratio so critical right now?
Well, it matters hugely because that difference, the net energy you gain, it's actually shrinking for a lot of our traditional sources. Global energy demand is climbing, but the EROI for fossil fuels, it's been falling quite dramatically.
You have numbers on that.
Yeah, I mean, look at U.S. oil. Back in 1954, the EROI was estimated around 24 to 1. Pretty good.
Okay.
By 2007, it had dropped to just 11 to 1.
Wow. So more than halved. You're spending way more energy just to get the same barrel of oil out.
Exactly. It takes much more effort energetically just to stay in the same place.
And that reality, that declining net energy from old sources, it forces us to look really hard at alternatives like PV.
Yeah.
But not just if they work, but if they're genuinely getting better and more sustainable over time.
Right. You can't just take a snapshot from 5 years ago and assume it still holds true. You need to see the trend.
Which means looking at the history.
Yes, and that's what this 2016 study did. They needed a model to project forward, so they went backward first. They gathered accumulated energy demand, CED data from 73 different publications,
73. Okay.
spanning from 1976 all the way to 2010. So decades of information.
It's a serious amount of data collection. Must have been a huge task.
It really was. And they were strict about it, too. They only used studies with full life cycle analysis, LCA data. I mean, they looked at everything from mining the initial silica sand all the way through manufacturing the cells, assembling the modules, the system itself, and even thinking about recycling. All the direct and indirect energy inputs.
Okay, comprehensive. Now, you mentioned the core idea, this leap they made. Applying financial learning curves to energy. How exactly did they swap costs for energy?
Well, conceptually, it's pretty straightforward, but proving it works takes a ton of data. They took the standard learning curve formula.
Which says cost drops predictably with cumulative production.
Right. And they just replaced the financial cost variable with the cumulated energy demand number, the CED value. They were essentially asking, does the energy budget needed to make a solar panel behave like its price tag does over time?
Treating joules like dollars, in a way.
Kind of, yeah. Creating an energy learning curve. If it worked, if energy reduction followed that same pattern, they could use this well-established economic model to forecast solar's energetic future.
And they track this across the main PV types.
Yes, 6 major technologies at the time. You had the silicon-based ones, single crystalline, multicrystalline, ribbon silicon, and then the main thin film types. Amorphous silicon, cadmium telluride, or CDT, and CIGS, copper, indium, gallium diselenide.
Covering the whole market, basically.
Pretty much. But, looking at that historical data, especially going back to the 70s and 80s, they ran into a big challenge with data consistency, particularly around the silicon itself.
Ah, yeah, the source of the silicon changed significantly, didn't it, around the year 2000?
It did, and that caused a real headache for comparing energy costs accurately over time. It wasn't just a minor detail, it was potentially a major source of error if they didn't handle it right.
What was the issue exactly?
Well, before about 2000, a lot of the silicon used for solar panels was actually off-spec stuff,
Yeah.
basically waste material, leftovers from the microelectronics industry.
Okay, so it was cheap, maybe even free energetically in some analyses.
So that was the problem. Since it was considered waste, many of those older LCA studies didn't fully account for the energy that went into producing that silicon in the first place. They just started the clock when the solar company got the waste.
Which would make the energy demand in those early studies look artificially low.
Exactly. Then, after 2000, the solar industry got big enough to need its own dedicated supply. It shifted to using purpose-made, solar-grade silicon, or SOGSI.
And producing that takes a significant amount of energy.
A very significant amount. The study highlighted that for multicrystalline silicon especially, making the silicon feedstock could be over a third of the module's total energy demand. So, if you ignored that properly in the later data or didn't account for its absence in the early data, your whole trend line would be skewed.
So how did they fix that? How did they make the old apples comparable to the new oranges?
They used a clever approach. To smooth out the influence of those potentially incomplete early studies, especially before 1995 when good data on multicrystalline silicon was really scarce, they calculated an annual weighted average CED across all SLIS technologies,
Weighted by what? Market share.
weighted by the installed capacity of each technology in that year. This way, the average CED value for any given year better reflected the actual energy intensity of the PV that was being deployed then, correcting for those data gaps and inconsistencies.
Okay, makes sense. So they cleaned up the data, applied the learning curve model. What was the big result? What did they find?
The bottom line number, the overall energy learning rate for the entire PV module market combining all types, weighted, from 1974 to 2010, they found it was 17%.
17%. So for every time the total amount of PV ever produced doubled, the energy needed to make the next module drop by 17%. Sounds pretty good.
It's very good, especially consistently over decades.
And where were the biggest energy savings happening? Which technologies were learning fastest?
It was mainly the traditional crystalline silicon modules. Multicrystalline silicon, MCSI, was the star, showing an energy learning rate of 24%. That's huge. Single crystalline CSI was also strong at 18%.
And what drove those big drops?
Mostly it was down to constant improvements in making the silicon itself more efficiently, better processes, less waste, scaling up production.
Okay, what about the thin film technologies? You mentioned CDT was lower, around 7%. Why was that?
It wasn't that they weren't improving. It was more that thin film technology started out needing relatively less energy to begin with compared to the silicon wafers. So the percentage drop wasn't as steep because the starting point was lower. There was less room for massive percentage gains.
Ah, okay. Less headroom for improvement on that metric.
Exactly. And the study also pointed out something interesting about how they improved. They looked at the learning rate based on module power output versus the learning rate based on module area.
Right, because efficiency plays a role. Getting more watts out of the same size panel.
Precisely. For the thin film modules, a big part of reducing the energy cost per watt came from boosting the module's efficiency. You get more electricity for roughly the same energy input in manufacturing.
Makes sense.
But for crystalline silicon, while efficiency gains helped, a larger chunk of the energy reduction came from just making the manufacturing process itself leaner and more energy efficient, even if the efficiency didn't jump as much in a given year. They were getting better at building the physical thing with less energy.
Two different paths to energy savings then.
Kind of, yeah.
Yeah.
And we should just quickly mention CAGS, the copper indium gallium diselenide. It was the newest tech in their data set, so they just didn't have enough historical data points to pin down a reliable, constant learning rate for it at that time.
Fair enough. Okay, so that covers the modules themselves. But a PV system is more than just the panel, right? What about all the other stuff, the balance of system?
Ah, yes, the BOS. This is where things get, let's say, a bit less exciting in terms of progress.
The BOS being what exactly?
Everything but the module. So the inverter that converts DC to AC electricity, all the wiring, the mounting racks, the foundations, installation labor, energy, everything else you need for a working system.
And how fast is the energy cost of that stuff learning?
That's the kicker. It's barely learning at all. This study found extremely low energy learning rates for BOS components, like basically flat.
How low?
Try 0.3% for ground-mounted system BOS and 0.4% for rooftop BOS. Almost nothing compared to the module's 17%.
0.3%. So the energy cost of steel racks and concrete foundations hasn't really changed much since the 70s.
Pretty much. This is what they called the BOS drag. The rapid energy savings happening in the module factories were being significantly dampened, or softened, as they put it, by the stagnant energy cost of the rest of the system hardware.
Okay, so the modules are racing ahead, energetically cheaper all the time, but the frame and fixtures are lagging way behind.
That's the picture. So when the researchers put it all together, the improving modules and the slow-moving BOS, weighted by market share for whole systems, the overall energy learning rate for a complete grid-tied PV system came out to be 14% for that 1974-2010 period.
14% total system learning rate. Still pretty good, but pulled down from the module 17% by the BOS.
Exactly. But here's where the study delivered its most powerful punchline, I think.
Go on.
They compared that energy learning rate of 14% for the total system to the financial learning rate for total PV systems over the same period. It was also 14%. And remember, the module-only energy learning rate was 17%.
Yeah.
The financial learning rate for crystalline silicon modules alone was also 17%.
Whoa, okay. That's remarkable. The energy reduction physics tracked the financial cost reduction almost perfectly.
It was an incredibly strong correlation, and that was huge because it validated their whole approach. It showed that, yes, you can use these economic learning curve models to understand and, crucially, to project the future energetic performance of solar power.
Okay, so they proved the model works. Let's talk projections. Using that validated 14% system learning rate, and assuming I think they used a 30% annual growth rate for the industry,
Right.
what do they predict for 2020, looking forward from their 2010 data? Let's start with the energy payback time, the EPBT.
Right. So back in 2010, based on the tech status then, the worldwide average EPBT was calculated to be somewhere between 1 and 2.5 years, depending on location and system type, of course.
Okay, 1 to 2.5 years to pay back the manufacturing energy.
Yeah. The projection for 2020, using that 14% learning rate, was that the EPBT would drop significantly down to just 0.5 to 1.5 years.
Half a year. So potentially, a system installed in a sunny spot could generate back all the energy used to make it in just 6 months.
That was the projection. Really quite amazing progress.
And what did that do to the EROI, the energy return on energy investment?
That went up dramatically, too. For 2010, the EROI was estimated between 10 and 25. Solid, but not spectacular, maybe.
Okay.
By 2020, the projection showed EROI rising to 20 to 60.
20 to 60. So getting potentially 60 times more energy out over its lifetime than was put in to make it.
That's what the learning curve model predicted based on continued progress.
Let's just pause on that. An EROI of up to 60. How does that compare to other energy sources? You mentioned oil was down to 11.
Yeah, exactly. It puts PV, or at least the projected 2020 PV, way up there. It's comfortably in the range of wind energy, which is typically cited as 15 to 40.
Better than oil and gas, better than nuclear, which is often cited around 5 to 15.
Definitely. The only major source consistently higher is large-scale hydropower, which can get EROIs up around 100, but obviously has geographical limitations. So this study basically charted PV's path from being just promising to becoming potentially one of the most energetically productive sources we have.
Okay, so let's wrap this up. Summing up our deep dive into that 2016 paper, Energy Learning Curves of PV Systems. The really big takeaway seems to be that it was the first to rigorously show that the energy needed to make PV follows that classic log linear learning curve, just like financial costs do.
Exactly. The physics mirrored the economics, and the rate of that energy improvement was, and presumably still is, rapidly boosting solar's overall energetic viability.
And that high productivity, the shrinking EPBT, the soaring EROI, that's absolutely crucial, isn't it, for actually making the energy transition happen and tackling climate change. It justifies why PV is grabbing such a large market share globally.
Absolutely. The numbers show it's becoming an incredibly efficient way to generate energy, not just financially, but thermodynamically.
All right, let's leave our listeners with a provocative thought, building on this study. The research clearly pinpointed the balance of system components, the racks, the foundations, the inverters, as the main drag on further energy improvements because their learning rates is so low.
Right, the modules improved massively thanks to breakthroughs like dedicated solar-grade silicon. The BOS, not so much.
So here's a question. What equivalent breakthrough is needed for the BOS? What kind of radical innovation, maybe in materials for the mounting hardware or maybe completely different ways to install foundations quickly with less energy, could slash the energy cost of the BOS and push that total system EROI well beyond 60, maybe even towards hydro levels?
That's a great question. It really forces you to think about where the next big leap in solar sustainability might come from. It might not even be in the panel itself anymore.
Something to chew on. Where's the innovation hiding in plain sight? We'll catch you next time for another deep dive.